Hello, welcome to another Physics 4B lab. We want to talk about electric potential and its relationship to electric field today. I hope that we're covering, at least we started to talk about electric potential in our regular lecture class. So we know about electric field by this time, that you have a charge and then you have the field which emanates from it. And we consider if you have a positive charge, we take it to be that the fields are going out of it. And if you have a negative charge, fields are coming into it. So, so if you're looking at just the electric field, so let's look at this first. So you have a positive charge, and you have field lines originate from the positive charge and go out from it. As I said, that this is our convention, actually. We could have taken it that the lines are going into it, but our convention is that it goes out from it. And if I look at a particular point over here, let's call it point P, and the distance from the charge is R. Don't get confused with this big sphere. It's just a point, actually. So the electric field over here would be, it's a vector going into the R direction. It would be the charge itself, 4 pi epsilon naught R square. If you want to use a vector sign, then I will have with an R cap. That's a unit vector with a magnitude of 1. Basically, it says that the direction of the electric field at point P is towards the R direction. So it's a vector right there. So we take the charge, divide by R squared. That's the main thing. And our, our unit here is simply Newton over Coulomb. The way I look at it is that if you had another charge here, let's say another charge of Q, let's say, then the Coulomb repulsion or attraction between them would have been Q times Q over 4 pi epsilon naught R square, and the unit would have been Newton. But if I divide F with Q, okay, so I have a charge Q here, but what kind of electric field does it experience? It experiences that. There's one less Q, right? So E is nothing but F over Q, where Q is the charge that I place over here, okay? So that's the electric field that I experience. Now, if I actually bring a charge Q from infinity or from anywhere, actually, and put it right here, I have to overcome, let's say this charge is positive, I want to bring another charge over here. So this charge has to overcome the electric field repulsion, and I have to put in work into it. So when I put this charge over here, I've taken it from wherever it is to here, I have put in work into that. And that means that in this combination, if I have two charges, I have put energy into the system. So what's the energy in the system? The energy in the system, I will call it U. So this would be called electric potential energy. So what's that electric potential energy? See that over here? So basically, I have Q times Q. I have 4 pi epsilon naught R square. And then, because I have brought it from somewhere, I have to multiply it with some kind of distance. Okay, I'm simplifying it right now. I need to do an integration to do that. But my point here is that I can simply write it out as 4 pi epsilon naught R. And the unit of this would be simply joules. Okay, simply joules. So I want you to notice what I did here. This is Q square over R square. Okay, this is Q square over R square. Right here, it's simply Q over R square. This one here is q square over r. That's the, if I bring another charge over here, so I have to fight the repulsion force, so I put energy into the system, and so that's the q charge. I am bringing it from infinity or wherever it is to that point. So that's the energy that I have right now. Now what happens, the last thing that I want to talk about is potential. What this, see that electric potential energy, I divide U by the q charge that I brought from wherever to this point, okay? And then I divide the energy by this q, and what I get here is simply q over 4 pi epsilon naught r. That's an r, by the way. So I take the energy, divide by the charge that I brought from somewhere else to that point. I get q over 4 pi epsilon naught r, and I define the potential right at that point. And you can see I can write it out in many different ways. Sometimes we simply call it volts, but you can see what volts is. It's basically joule over coulomb, and that we define as volt. Okay, volts. If I go back and look at the electric field, and I compare this with that, you can see that I have an extra R on the bottom for the electric field. So if I take my volts, I divide by meter, I can get electric field. So there are several ways of looking at electric fields. The two ways would be just take the Newton, divide by the Coulomb, so it will be Newton over Coulomb, or you can define it as volts over meter. And I want you to remember that. The electric field is either Newton over Coulomb or volts over meter. These are the four fundamental concepts for static electricity. You have force, which is a vector, electric field, which is a vector, electric potential energy, which is a scalar, and potential, which is a scalar. This is the, in our day-to-day life, this is the one which we are most familiar with. We don't talk about Newton, we don't talk about Newton over Coulomb or volts over meter, we don't talk about joules, but we do talk about volts all the time. You have a battery, and the battery is a 5-volt battery. This is we call the positive and negative terminal. What we do when we make the battery is that there are chemical stuff inside, we know that, but we have to achieve charge separation within the battery so that one side gets positively charged. You know, we kind of separate out the positively charged and accumulate it there. The other side is negative. What we have done literally is that we have given potential energy to the system, okay? And then we divide by the charge, we get the volts. Let's say it's a 5-volt battery, but it's not that one side is 0 volt, the other side is 5 volts. Actually, we really don't know. All we know that, for example, this of the top could be, for all you know, it could be 15 volts with respect to, this 15 volts with respect to some known voltage point. What do I mean by that? It could be 0 at infinity, for example. Okay, 0 at infinity. For all you know, the negative side could be minus 10 volts, again with respect to some known voltage point 0 at infinity. What's the difference? 15, sorry, this would be plus 10 volts. The difference is 15 minus 10, which is 5 volts. These voltage points are actually floating if we don't actually measure it with some known point that we consider to be 0. Again, if it is 0, it is 10 volts with respect to that. Not necessarily that 0, by the way. We consider it to be 0. That also is kind of a floating point. We just decided that to be 0. and this is 10 volts above that. That's 15 volts above that. So if we now connect these 2 points, a current will flow out from here. What literally will happen that is that because that's more positive than this guy, electrons will actually flow out from here and go to the positive side. And before, in 19th century, we did not know really that what is positive and what is negative. And so it was decided basically that if this side is a higher potential, current will flow like that. But now we know that actually it's the electron flow which defines the current. If they knew at the time, I'm sure that the electric current would have been defined the other way around. But right now, we define the electric current opposite to the electron flow movement. So anytime you actually connect this higher potential to lower potential, you actually have the current flowing. Why do we use voltage and not any of these other things? It's because electronically, it's the easiest thing to measure. And I don't want to talk about it right now. And I'll show you something called a digital multimeter. And this is the reason why we need to be in the lab, so that you can actually get to know the use of digital multimeter. This has multiple functionality. And the 3 functionality that we definitely use, one is to measure resistance, right? One, we measure resistance, which is defined by the omega sign, which is ohm, okay? Then we define the voltage, which is the potential difference. But notice that it has a direct current symbol over there with those 2 lines. So it is voltage where the current is not changing direction, not AC, but DC, direct current. And also with an A, that's an ampere. So when you go over here, is basically you are going to measure current in the units of ampere. But you notice that these are very small numbers, which is 200 microamp, 20 milliamp, and 200 milliamp. And the current, you don't want to have very large current in your circuit. So that's, that's one side. And then the other side, you will have the variable voltage and variable current. And they actually measure root mean square voltage and root mean square current if the current is AC, alternating current. So going back to it, the reason voltage is very easy to measure using Ohm's law. And the Ohm's law, I'm not going to talk about Ohm's law right now. It's basically if you have a voltage difference between 2 points and there is a resistance, when you connect those 2 points, there is a resistance. And then the current there is defined by voltage over the resistance. So the voltage is simply current times resistance. So there are resistors in this voltmeter. And by simply measuring current and multiplying by the resistance, you can get a voltage. So electronically, voltage is a very good thing that I can measure right away. It's much more difficult to measure force or electric field or even potential energy, actually, whereas voltage actually measures very easily. And in some electrostatic cases, sometimes we measure voltage, and then from voltage, we actually go back and measure the electric field. So there are a lot of practical advantages of actually using voltage among all other these 4 parameters that I mentioned. So today's lab, what we want to do is we're going to put voltages at different points of this. This is a conducting paper, and basically there's kind of small metal particles on it. And then what we have is we have a conducting pen, and we draw these with this conducting ink. We actually draw these barriers. So what happens here, and then we put actually electric current or potential at a particular point, and then we want to trace out electric field by using the voltmeter. And you say, how you can trace electric field with the voltmeter? Well, let's think about this way. Let me go back here. So let's say that this distance from here to here is A. Okay, so what's the voltage here? The voltage at point A is simply, if I go back and look at my formula over here, it's Q over 4 pi epsilon naught A, right? And then I measure a point over here, voltage at point here. VB would be Q over 4 pi epsilon naught B, okay? So let's say this is 4 volts and this is 3 volts. Okay, so it's dropping because B is larger than A. So obviously potential at B would be lower than the potential at A, right? So what I know right away that if I just simply do VB minus VA divided by the distance between them, which is B minus A, that would be my electric field actually. The only difference is that the electric field direction is going from right to left, and the electric field will gradually drop, of course, but it's not in the negative direction, so I just have to put a negative sign in front, which is all right. Okay, but the main thing here is that I have to measure the voltage difference between these 2 points and divide by the distance. That gives me the electric field. If I go back here, remember I have volts over meter, that I measure the voltage and divide by the meter, which is the distance. So that's what happens here. So let's say that the distance between them is, I'll just make something up. Let's say distance is 4 millimeter. Okay, 4 millimeter. So the electric field in this case would be minus 3 minus 4. And what's 4 millimeter? 4 millimeter is 4 times 10 to the power minus 3 meter. So what do I get here? This is minus 1 on the top, 4 times 10 to the power minus 3. So that would be plus. So this is 1 over 4 is 0.25 times 10 to the power plus 3. So it will be 250 Newton over Coulomb. That will be my electric field. I can measure the electric field right here. It's 250 Newton over Coulomb. It's going to the left. That's why I put a negative over here so that I get the right direction. So what will happen here is if I measure the 4 volts over here, and that 4 volts, you'll see later on how I'm going to measure it. So this is my voltmeter. And I have to measure this over, let's say it's 20 volts scale. And this is if I just put it over here, this is floating. I will not get anything out of there. But I have to know something that is 0 volts. So basically, it's over here, it's grounded. So now I should get 4 volts over here. Okay? Obviously, I don't have any potential over here, so you will not see anything down here. But so that's there. And then I will go over here. That gives me 3 volts, right? So this will be so that's one way of doing it. Or the other way of doing it would be simply, this is the positive terminal. I simply put it like that, and I should, if there was really, electric charge in this process, I would have seen the difference right there, a 1 volt difference between these two. Okay, and then I divide by the distance. I get the electric field. I go there. So then my idea would be, if this is 4 volts, and I go around like that. Okay, so for example, if I get 2 volts over here, electric field, again, remember the electric field would be the most rapid kind of incline that I'm looking at. So what will happen here is this. If I look around within 4 millimeter, let's say, and I have to find out the point which is the lowest. So for example, if this is 3 volts, and this is 3.5, that's 4, that's 3.9, and so on and so forth, the electric field direction would be like that way. Okay? But, so this is my point here. This is 3.5 volts. This is 3.9 volts. So those are not the electric field direction. I come over here, and I look for the next steepest decline. So for example, I get here 2, I get here 1.8, I get here 1.9, I get here 0.9. So really speaking, I'm making this up. Of course, it will not be like this. Then my electric field will be in that direction. So it's basically the steepest decline that I need to find out. So actually, the thing will start to bend right like that. And you say, what about this point? Well, obviously, there will be a point here. In some ways, some other field lines will come through here, but it will be difficult to map it like this. But that's our idea. That's how I'm going to look at electric field in this experiment. Sorry for this mess over here. I hope you got the idea more or less how we are going to do this. Couple of things is that if you are, let me just do this separately. I'm going to erase this. And so let's say you have a sphere like this, right? And you have a charge over here, which is Q. What does that mean? I'm going to put charge over here. I'm going to connect a line from the battery to this point, and then this line would have electric field going out like this. And what will happen is that this induces, let's say, negative charge over here, okay, which will induce positive charge over here, right? So when I'm outside, I'm looking at an electric field at this point, and the distance is r. This would be simply E equals Q over 4 pi r square. The electric field, as you go up to this point, will start to go up. Okay? Okay, my apologies. The electric field will start to go up. So if I draw a graph, this is, let's say that the radius is A. So my electric field is this on the y-axis, and x-axis is the distance. This is r. And the electric field will go up as I come close to the radius. So this is my kind of highest point over here. So E would be at point A, E would be Q over 4 pi a square. Okay, very good. Now you say, what's the electric field inside? Well, the electric field inside we'll be talking about in the class actually would be literally 0 in some ways, because the positive and negative over here would cancel the original electric field. And so this would actually kind of literally drops right there, okay, electric field. Sorry, let me backtrack a little bit. Actually, I don't want to put a charge over here. Let me take the charge away. I don't want to put this. So my original charge was, because that was a little bit extensive, the original charge was put on the outside of the sphere. That's what I wanted, actually. This is the part I wanted. So what does that mean is I have connected it to the positive terminal of my battery. So I have only put positive charges around the sphere. And now inside, the electric field is 0. This is the important part here. Let's forget the other part. So the question is, what would be the potential inside? That was the question. The potential over here is Q over, sorry, I need an epsilon naught. I need an epsilon naught here. 4 pi epsilon naught r. When I come over here, what's my potential here? My potential here would be Q over 4 pi epsilon naught a. The electric field inside is 0. What's my potential inside? And this is one of the things we're going to find out. Turns out potential inside is not 0. Potential inside would be Q over 4 pi epsilon naught a. The same potential. And because there is no potential difference, your electric field will be 0. So if I put 5 volts over here, it will be 5 volts everywhere inside. Even for a sphere, you have a metallic sphere, you put charges outside, inside the electric field will be 0, but the potential field will be constant. So the electric field goes down to 0 over here, but for the potential V, this is what happens. It kind of drops outside as 1 over R, but right here it becomes constant right there. So which is basically Q over 4 pi epsilon naught A. So this is the thing we want to actually verify today, that if you put a 5 volts to a ring, outside the voltage drops, but inside the voltage is constant. That's one of the things we need to find out. And that, I think, is something great, actually, we need to do. All right? Forget the first part I said. Actually speaking, we're also going to do when you have a charge inside. Okay, when you have a charge inside, and that actually induces negative charge here. And when you look outside, the electric field should be 0. That was the idea. Electric field, in some ways, that this electric field actually terminates over here. And that we called a safeguard ring, or a guard ring, actually. So this is one of the things we're also going to encounter if there was a simple line like that. All right. Okay, so I will stop right now, and we will actually look at what you call it, look at the write-up a little bit, and then we'll go to the main experiment. Okay? Okay, here we are looking at our write-up. So these are the material. If you're here, we could have used. But let me go to look at a couple of things. So one thing if you look at, it says that there are the paper that we're going to use, the black conductive paper, it has carbon in it, and the resistance, there's some resistance, 5 to 20 kilo ohm per square, relatively reasonable resistance. And then the paper forms a conductive medium or space between electrodes. The second element is a conductive ink dispensed from a pen. The ink is produced from silver particles in a suspension liquid. I don't know how many silver particles are there. It's not much, actually. You don't need many particles to make it conductive. As the ink dries, the silver flakes settle on top of each other, forming a conducting path or conductive ink electrodes. The resistance of the ink is between 0.03 and 0.05 ohm per centimeter for a 1 millimeter wide line. So you can see the resistance difference between the silver ink and the paper. The paper has much more resistance than the ink itself. So you can almost think of the ink as the conduction is very high. So if you, on that line, if you put if you put charge on it, the charge will be distributed across the line, so it should be in the same potential. Because the paper has a finite resistance, a current must flow through it to produce a potential difference, and that's very important. This current is supplied by the conductive ink electrodes, which causes a potential drop to occur across the paths. Because of the large difference between the ink's resistance and the resistance of the paper, this potential drop is less than 1% of the produced across the paper. So again, the potential drop across the electrodes may be considered negligible. Well, again, what I meant is that what I said before is if we have the ink line, within the ink line, there shouldn't be much potential difference. Unfortunately, we always get some potential difference because it's very difficult to actually draw those lines. And if you're in the lab, you would have known exactly what I meant. Now, to plot equipotentials, charge and field gradients, you will need a voltmeter or other potential measuring device. We talked about the voltmeter. It would be desirable that the potential measuring instrument have an infinite impedance. That's always not the case. Let's not worry about it for the time being. Our digital multimeter has more or less 10 mega ohm, which is okay for our purposes actually. So let's look at what we really want to do. This is how actually you draw the line. So we don't have to worry about it because you are not here and drawing the line right now. But this is the part which actually we want to show you, because because we are going to use a DC power supply. We have a power supply, right, Hawaida?
Yes.
Okay. Yeah, right. We need a DC power supply. And what happens here is that you have, you can actually produce current. This is a direct current, and you, for example, you draw these lines over here as a circle, and that's a line. So what will happen here is you would put, let's say you put plus 5 volts here and 0 volts here. It literally would mean that this is positive and that's negative. All right. So what will happen is that electric fields will come out of the positive side, and it will actually end up on the negative side here on this circle. But again, remember I said about the safety kind of this, there will be no kind of a safeguard. This is a guard ring, and we will figure out what you expect as potential inside, or what you actually expect with the electric field inside right here. Okay, so this is one thing we are going to experiment with first, so that we are getting the right thing. So what is the equipotential? If we go back and look at this figure here, it's a dipole. We'll have, let's say, plus 5 volts here, 0 volts here, and the electric field lines will go from the positive side to the positive point to the negative point. The electric potential, equipotential lines will be always perpendicular to the electric field lines. Okay, so it will be perpendicular to the field lines. So if I come over here, maybe if this is 5 volts and this is 0 volts, and if I gradually go up here, it will drop with respect to that. It's like 4 volts and then 3 volts, and then if I go up here, 4, 3, 2, 1, 0, it'll come to 0 right there in the end. Okay, or if I want to go from left to right, this would be 5 volts, 4 volts, 3 volts, 2 volts, 1 volts, and 0 volts between 0 volts over here, because you're looking at the voltage differences. So again, when I will do this, I will show that to you. And this lab is more or less in demonstrative purposes, so that you, I'll give you some assignments later on in class, but you have to kind of look through different configurations that we're going to use to plot out the equipotential lines and the field lines. Okay, so let me just look at here, plotting field gradients. Sorry, one second. Equipotentials are plotted by connecting one lead to of the voltmeter to one of the electrode push pins. This electrode now becomes a reference. The other voltmeter lead is used to measure the potential at any point on the paper simply by touching the probe to the paper at that point. To map an equipotential, move the probe until the desired potential is indicated on the voltmeter. Mark the paper at this point with a soft lead or colored pencil. So basically, we're looking at two different potential points. The difference is whatever the potential we want. Let's say we want the 5 volt potential difference or 4 volts potential difference. So let me go back and show you what I mean again right here. So see this right here. So the difference from this point to this point would be possibly, I don't know, maybe 1 volt, because this is a 4 volt point and that's a 5 volt point. So, and then this is 5 volt, my reference point. So when I put it here, this would be only 1 volt difference, because this is a 4 volt point. So then I come over here, I get 1 volt, I get 1 volt here, I get 1 volt here, 1 volt. And so that would be my equipotential circle. Similarly, if I go over here, the difference between that point and that point would be 2 volts. Here it would be 2 volts, that would be 2 volts, 2 volts, 2 volts, and that would be my equipotential line, right? So those are the equipotential contours. That's what's meant by that write-up. So, and the field gradients is a little bit difficult. That means I'm looking for the electric field lines. You'll place 2 leads of the voltmeter side by side at a set distance, 1 centimeter. Best to have 2 leads together for the procedure, like here. And then to plot the field lines, place the voltmeter lead ground, connected to ground near one of the dipoles. Place the other voltmeter lead on the paper and note the voltmeter reading. Now pivot the lead to several new positions while keeping the ground lead stationary. Note that the voltmeter readings as you touch the lead at each new spot on the paper. And then when the potential is the highest, draw an arrow on the paper from the ground lead to the other lead. This is what I meant actually, that you look at the steepest descent or the difference would be the highest. Then move the ground lead to the tip, repeat the action, pivoting and touching the front lead until the potential reading in a given direction is the highest. So you're always looking at the steepest descent of the electric field, which will give you the highest potential differences. And hopefully you will get to draw something like that. I will try to do this for you and see how much I'm successful or not. So we do we'll start with the dipole that we showed at the very beginning, and then we're going to go through several geometric configurations. We'll have the parallel plate capacitor, point source, and the guard ring. We'll have the dipoles of opposite charge. That we'll actually start with that. Dipoles of the like charge, floating electrode, and I think we're going to go at least up to experiment 6. And let me see if we get some figures already done for experiment 7 or 8. So we will at least try to do up to experiment 6. And if we have time, we will actually go through experiment 7 and 8 also. Okay, so that's our write-up. Now I'll go over to the experimental setup. All right, so here we have, you see this is the carbon resistance. There's some resistance here, but it's conductive paper, but has high resistance compared to the silver ink pen. And I'm trying to make a dipole. So what I have here is that I'm going to put some conductive ink over here. This would be my maybe positive or negative. Okay, so that's over here. And then over here I need another point. It would be, if the right side is positive, then the left side is negative. And so I want to make sure that I have enough ink here so that it conducts well. In that splotch, the blob, the current should be equally distributed, or the charge should be equally distributed, I must say, so that I get the same potential over here. So we'll find out. This is one of the, if you're here, I'd have said the most difficult part of this lab is actually get this ink flowing out of the pen and actually get a proper conductive layer. Let me see if I am successful. If not, I have some old paper that I'm going to use. And so this is also would be a conducting pin. Okay, a conducting pin. And I'm going to, this will be served as electrode. And we'll find out in a second that if this method worked. So, so I'll have this over here. This would be my positive, and this would be my negative. What I have as a power source is a DC
power supply, and you have the voltage and current that you can regulate. So let me see if I can put in about 5 volts here. Let's say I have about 5 volts over there. We can see that, right? Over there. So that's 5 volts. And so these 5 volts, it means that basically I'm putting some current over here, charge over here. And there is current if there is enough, what do you call it, conduction through here, there should be current, but I'm not sure if the conduction is made. So first of all, if I look at between these two positions, be 5 volts. If I go over here, sorry, I need to show you where I'm measuring it. So I'm measuring it over with this voltmeter, okay, and if I am looking at this way here, how about that?
A little more south. There you go.
All right, good. So good, that's good. Okay. Yeah. So let's see what this gives me. If I get 5 volts difference between them, there's a 5 volts difference, as you see, and my knob is at 20. Maximum I can measure is 20 volts in the direct current voltage measurement. So that between them is 5 volts. So now I want to go over here and see if I can measure something. That's 3 volt difference. That's 2.6 volts difference. That's 1.67. That's 1 as 0.89. And then as I come close here, up to here, I should get 0 volts because I'm measuring the same place. So before I move on, I want to kind of get this idea. Between this point and that point, the voltage difference is 5 volts because that's my kind of 0 volt difference because I'm giving out a 5 volt difference. So between that red electrode and that black electrode, the difference is 5 volts, of course. If I take this to kind of infinity or some grounding material, right over here, I'm not getting anything over here because basically this is not a conducting thing over here. So let me check one more time. This is 5 volts difference. See that this is 2.5 volts difference over here because there are electric fields going around this place. Okay, so I can go at different places. So when I put it over here and the difference is let's say it's 2 volts difference. What that means is that the red point is 5 volts with respect to 0 volts. And this point by itself, the black side, by itself would be 3 volts with respect to some other point. So 5 minus 3 gives me 2 volts. That's the idea. Okay. So again, because of the conduction differences or how I am looking at it, this thing is not linear. It should have been linear. Or it falls away as 1 over r, actually, not linear. I shouldn't say linear. 1 over r. So again, right here, the difference is very low. It means if this is 5 volts, this would be 4.3 volts or so, 4.4 volts. Then over here is about 4.2 volts. Over here, the difference is 1.2, so this should be 3.8 volts. Over here, the difference is 1.5 volts, so that would be 3.5. Over here, the difference is 2.4, so this would be 2.5. Then over here, it's 2.5, and then it drops, so 3 points, so there'll be 1.5. And right here, it actually goes to 0. You see so that would be how the voltage drops. Now, if I'm looking for the equipotential line, if let's say that I have, so this difference is, let me find out a point, so the difference is 1 volt, right there. So I'm going to find out all 1 volts line around it. So it will be really a circle around that point. See that it's kind of close to 1 volts, so 0.86 or something right there. See that 0.86. So it will be closer a little bit to here, because again I said that the conduction is not conducting properly. So, but you get the idea. So this will be a circle around it. So that would be somehow I can actually draw my equipotential lines. So let me try to draw some equipotential lines for you. All right, and we got a pen. I think we can just to draw those equipotential lines. So let me go back and look at any point which is, let's say, 1. Oh, I think, Hawaii, I might need some help over here. So what I'm going to do is that I'm going to find out that 1 volt difference. So remember, this is 5 volts. This possibly 4 volts over here, and the difference will be 1. So what I will do is that I will have you just hold it over here, right there, just touching that the main electrode here, right there.
Okay.
And then what I'm going to do, I'm going to find out this 1 volt, 1 volt potential difference around it. So that's, for example, that's 1 volt right there, okay, and then right there is 1 volt. That's about 1 volt here. I would say that's about a volt here. That's about a volt here.
If I do this, would not hold it? So I'm not
Yeah,
in your
go
way.
ahead. Go ahead. It's sometimes hard to make contact. Oh, that's good. Thank you.
Yeah, I didn't want to be in your way.
That's fine. That's good. That's fine. So then 1 volt here. And then we at least want to do at least 1 circle here and 1 circle on the other side to show you. So that will be 0.9, and that will put 1 volt here. It almost seems like I really have to go out quite a bit. I cannot go any further out here, so I'll just leave it there. And then this one would be, as you can see, this one actually goes out a little bit. So you can see how it's a symmetric circle. But it's not exactly a circle. It kind of goes out in the back. And the equipotential line will eventually meet on both sides. So that's, you can see that one there. So similarly, if I go over to this side here, so remember what I can do is this is a negative one. So what I can also put this over here. Let me see if I can do this the way you did that over there. And then take it out from here and see if I can measure the difference right there. You can see that the voltage difference. So I'm also going to, thank you, Hoeda. I will going to, so that's, let's say this is a 2 volt difference right here. So let me go with 2 volts. Right there, 2 volts. It's about 2 volts. So that's right, 2 volts here. It's kind of, it's only because our conducting, oh, this one died. Let's see. Hopefully,
This one, we have a plenty.
yeah, I have plenty. So let me get another voltmeter. This happens because of sometimes we got these batteries expires actually. So, but anyway, I wanted to show you one more time that when what's the we're using the voltmeter side here, and then they have the different upper limits that you use, and that uses different resistances. So thank you, that was great. So we have another voltmeter with a good battery. So I keep it here. It here, all right. So I need to, so that's my one electrode, and the other electrode is over here. Remember, we're looking for a 2 volts difference. Am I getting this? Mm-hmm. Okay. So let me go up to 20. So remember, that's about 1.8, 2 volts. So this 1.8 would be quite far. Let's see. So that's 1 volt. This is 2. And it drops very quickly. That's 2. That's 2, that's 2. So the 2 volts goes out like that. So basically there is a, over here, so this equipotential line is really large right there, okay? So let me see if I can get something smaller. So that's 1 volt, about 1 volt, 1.1. 1.1 here. So so 1.1 here. That's 1.1 here. Sorry for the mess. So you can see that I have, that has the equipotential line. It's more or less a circle, extended circle. It goes on the back side, it actually goes out a little bit. All right, so you get the idea of the equipotential lines as such. Ideally, this should be, you know, it just goes, it would be like that, and you have these circles going around for both of them, right? The last thing I want to do very quickly is, remember, this is the positive charge and there's the negative charge, the electric field lines, how the electric field lines are. So remember, electric field lines, the potential lines are perpendicular to electric field lines. The electric field lines will go from here to here. I just want to show a couple of electric field lines and see if we can succeed in that. So remember that if I simply go between those 2 points, see that the difference is, just have to make sure that is 0.26 volts, right? If I go up that's 0.12. If I go down with that, it's 0.06. I'm referring with respect to that where I'm touching with the red electrode. Okay, so in principle, this 0.2, that's my steepest descent. So then I come over here where my black electrode was and go to this next line, and this is 0.26. If I go up or go down, it will not be 0.26. So those are my steepest descent. Then I move my red pen over here and put my black electrode over here. It's 0.16. If I go up, it's 0.04. If I go down, it's 0.07. So the steepest descent is really in that direction. Then I move my red pen over here, put my black pen here, it's 0.38. If I go up, it's 0.04, go down, it's 0.03. So the steepest distance is that direction. So if I move it down, 0.53, 0.40, and so on and so forth, as you can see that it really increases down that way. So my electric field is literally going this way, but as it goes down, it the differences become larger in a sense that because the electric field becomes weaker and weaker. So the dropping is much higher compared to here. The electric field is stronger, then it gets weaker down here. Similarly, if I go from here is 0.33, I move over here and 0.18, 0.14, 0.27. Okay, so definitely I can find another place here. See that 0.34. So literally it goes in this direction. Then I move my red pen here, and that's 0.29, 0.25, 0.28, 0.31. So it will be in this direction. So you got the idea. So eventually when I look at the voltage difference, actually I will find out my electric field lines go like this way. On this side, if I had done it, my electric field lines would have been gone out this way, and then this would actually come and join over here. So you have the potential and electric field lines, they actually intersect each other at 90-degree angle. All right. Again, I'll just give you one problem to solve right now, which is if I look at the electric field, the potential difference between them is let's see, I started with a very high potential and then I dropped 0.26. So it's a 0.26 volts difference between these 2 points, and the distance between them is about 1 centimeter. So what's the electric field between these 2 points? So you have 0.26 volts difference, and the distance is 1 centimeter. What would be the electric field magnitude between these 2 points? See, you can find the electric field magnitude this way. Just simply divide 0.26 with 1 centimeter, which is 10 to the power minus 2. So it will be 0.26 divided by 10 to the power minus 2 gives you 26 Newton per Coulomb. Okay, so that's the electric field down there. So what I want to do is I want to actually show you, not necessarily go with the write-up, but it's there in the write-up at some point. I'm going to replace it now with already drawn couple of circles. So let me go with this one. I'm still keeping 5 volts as my original voltage. So let me put the conducting paper, place it on the cardboard. I want to do a couple of things with it and see what we get, and we'll try to see if we can explain it. Okay? The first one, I want to simply use the positive over here, okay, and then the negative over here, and see what we get. So we're going to, I hope there's enough conducting material here. If not, I have to put some. Let me go ahead and put some. I'm not sure this will still work. As you can see, they had a hard time. These are from my students over the last, I don't know, 6, 7 years. So we just kept this because we know that we'll have problem with the ink. And so the main thing is that there should be enough contact between the electrode pins and the board. Okay, but then the charge should be distributed over this conducting ink. As you can see, the charge should go all around this circle, homogeneously distributed. That doesn't happen all the time, but we try our best. So what I have here is I have a, thank you, I'll just get that. Okay, so we get the conducting pins on here, and then another one I'll put right outside. Okay, you always need 2 electrodes. You can't have it floating. So this one would be hopefully +5 in the center. We have not changed that at all. And then the current flow is really very minimal in this case. And then I have the difference between these two would be +5. Okay, +5. So so let me just first check that I got the +5 difference. So this would be between this and that. And I am not right there. So I got +5 difference. That's great. So now let's look at what's happening. That's 2.62, 2.9, 2.67, 3.93, 4.4, 4.5, +5. So the difference between the center point and the outside shell is 5. So here is my question. What do I expect outside this shell? Okay, so I'll give you 10 seconds to think about it. So again, I have between this point and so the electric field literally goes out from the center all the way to the edge, and the difference is +5. The question is that if I put my electrode outside here, what should it be? Would it be dropping further, or would it be 0? Well, let's figure this out. E got 4.45, okay, 3.560. Okay, 3.7, okay, 4.29. But if I look at these 2 points, 0. If I look at these 2 points, 0. If I come over here, I get always difference between 2 points. I always get non-zero within the shell, non-zero, okay? Within the shell, there is always some difference. Outside, I put this, it's all 0. What does that mean? Well, basically what it means is that the potential difference between these 2 points are the same. So whatever the potential difference here, remember this is 0, and I come over here and I put it here, that's 0, that's 0, that's 0. So whatever the potential is on the outside ring is the same thing over here. When I look from here, I mean, in principle, it should be 5 volts over here, actually. But, there is some variation as such. So that's 5 volts. And once that 5 volts, whatever that potential is, you have this outside paper is the same potential. Basically, I don't have any electric field outside here. And it makes complete sense, is because when I'm an observer from outside, you can think of it as a shell also with the charge inside. From outside, you have positive charge is negated by the negative charge. So from outside, with Gauss's law, I will see basically the charge is 0, and I will have no electric field outside. So there's no electric field outside, but the potential here is the same as the outside shell. Okay? Now I have to remind you, the potential of the outside shell is really not 0. It's 0 with respect to this 5 volts. Okay? But who knows? It could be 100 volts. This is 95 volts. So in a sense, if this is 95 volts, this is 95 volts all around it. If this is 0, this is 0 all around it. If this is -5, it's -5 all around it. So what's amazing about this experiment is that you can do this experiment in 2 dimensions, but it's true for 3-dimensional objects also. So again, I want you to imagine it as a shell, and you have a charge inside, and the shell contains all the electric field. There's no electric field outside. That's why it's called a guard ring. And the potential outside is the same. Whatever the potential is here on the surface is the same. So that's an interesting point. And if you draw the electric field here, the electric field would literally, of course, go out and would actually terminate on this thing, and there's no electric field outside. If you ask me what's the most important part of this lab, I would actually mention this particular one, where we actually literally show that the Gauss's law works, that you can imagine an artificial sphere outside, which we call Gaussian surface, and we count what's the total electric charge inside. The answer is 0, because that negates that. And so there'll be no electric field outside, literally. All right, so I'm glad that that worked out. So the next thing, I possibly will just do one more, and then I will ask you at home to draw all the electric field and electric potential for the rest of the ones that we couldn't get to today. All right, so let me use something here, like very quickly. I don't want to spend too much time on it. So there are a couple of things over here. We kind of combined, as you can see, we combined the guard ring with the center electrode. And we also has a parallel plate capacitor. The parallel plate capacitor by itself is a problem, as you would have seen from the write-up. So what I want to do is that this is an old paper with old ink. I want to make sure that we have some new ink here. Okay, so what we're going to do is we're going to simply put one of these electrodes, of course, on the right side. So let's say it will be plus 5 volts. It's a capacitor. It's a 2-dimension capacitor as opposed to a 3-dimension capacitor, but works exactly like 3-dimension capacitor. that's how you can model actually a lot of three-dimensional problem in real life with two-dimension setting, which is great. So you would know that if I didn't have the center object, the electric field lines will simply go from the positive side to negative side. It will be a straight line, except for at the corner where they can bend a little bit. But we're not going to concentrate on that. What I want to do very quickly to show that, first of all, I have that the voltage differences are 5 volts. Where is my red? Right here. So voltage difference is 5 volts. You can see that the 5 volt difference, right? That's great. And what will happen is that if I look at these two side points, it's about 5 volts, which is great. It's still conducting. That's great. And if I bring this gradually closer, that's 4.4, that's 2.93, 2.4, 1.83, 0.94. So in principle, the field lines are going here like that. The question is, what happens in the center? Okay, so look at this. This is 5 volts. So the difference right here is 0.9, so that is about 4.1. This is 4.1 volts, that's 5 volts, so the difference is, 9.9 volts. I go here, the difference is 1.4, so which is about 3.6 or something. I come over here, it's about 2 volts, so this is about 3 volts. I touch this guy, so that's 2.5. So this difference between that and that is 2.5, so fine. I touch over here, and I get 2.3, 2.5 almost. I touch over here, I get 2.3. I touch over here, I get about 2.4 or 2.3. I touch here. So the main thing here is that this entire circle, the charge is distributed, so it's in the same potential as opposed to that. If that is 5 volts, this is about 2.3 or 2.4 volts. The entire thing is 2.4 volts. Okay, that's number one. Number two, it's 2.4. So if I come here and I take any 2 points within the circle, I get exactly what we got before, which is within the circle, the potential in this circle is the same. So the difference between 2 points gives me 0. So if this is 2.4 volts or 2.3 volts, the outside ring, the entire circle inside is actually 2.4 volts. So that's most interesting part. And so then here, if I go from here to here is 0.69 and so on and so forth, it again starts to drop over there, okay, and so on and so forth, it drops. The question is that what's the electric field like? And this is the last thing we're going to do. So if you look at, this is 0.25, 0.20, when I come here is 0.11, it's 0.01, 0.06, right? So our electric field lines actually ends up over here, and then it comes out over here and goes on this side. Over here, the field lines actually skirts the central point. So it would be literally doing this, and then, or whatever, how that thing is, and then it will skirting that over there and go like that. And then again, it goes out from here. Okay, so that's a big thing about guard rings. So if you're going to do in future any electronic setup, you're going to draw some electronic boards, you will see this guard ring comes in where they don't want to have anything outside influence what's inside. It's almost like the mythological stuff where you draw a circle around you and you are safe in some ways. So it's literally that right there. So what I want to do is I want to stop right here, and at home, this is the part I'm going to discuss it later on in the class. I want you to kind of figure this out. If I just put a cut over here, what kind of electric field lines you expect, or the potential you expect right here, right, just like that. I can, if I have time later on, I'll show this in the class later on next year. Actually, I'm doing this in 2020, and your class will be in 2021. So, and what I want you to do is actually go through all the experiments up to at least experiment 8 and do this at home. And I want you to, when you submit the write-up, and those figures should be in there in your write-up. Okay, so I'll end here. I hope that you enjoyed it. There are several things, fundamental electrical properties that we went through that are really important, which we sometimes don't understand from our lecture. Thank you for being here. Bye for now.